start. Okay. So the whole point of this is to figure out the balanced equation for what's actually happening in real life. So we're going to start one at a time. And if you look at where it says data on the second page, I guess it is of this, it says using data tables or written descriptions, record observations for all reactants and all products, including evidence of a chemical reaction. So we probably need to talk about that. Evidence of a chemical reaction, light given off, drastic change in color, a substance appears or disappears, noise can be an example. So for each one of these, you want to have maybe what the reactants look like, what the products look like, and then a way that you can put evidence of chemical reaction. If you want to use a data table, but if you don't, you can use it as a description. And then you're going to include a balanced chemical equation for each one. So a before description, an after description, how you know that a chemical reaction happened, and then the balanced chemical equation. So I don't know how you want to set yours up, but that's what I want to see for all 6 of these. And that's what you're going to turn in for a grade. For an experimental grade, which remember, 25% of your grade. So if you want to, I don't know, write something now so you know what you're going to do. And I'm going to start setting up the first one for you, which is, I think I've done this before. We're going to burn magnesium. Except now you know a whole lot more. So magnesium is soft because I can rip it with my fingernails. And then I'm going to clean it because there's some tarnish on it. So you can see what it normally looks like. I have a little piece of sandpaper here. So if you look at the first reaction we're supposed to do, this is a synthesis. And we're starting out with magnesium, which is silver and shiny and flexible. Then I have my crucible tongs, my evaporating dish. Sorry. Wow, that's really high up. Well, we'll do what we can. So I'm going to light this on fire. If you look at part A, synthesis, obtain a 3 centimeter long piece of magnesium ribbon. That's what this is. 2, record your observations as to the appearance of the ribbon. Silver, shiny, flexible, we talked about that. Using the crucible tongs, hold the ribbon in the flame of a lighter. Note any change in appearance. Do not stare directly at the flame. I'm going to try to get it on the video without catching my hair on fire, which is always the main goal of a good day. See? There we go. The afterward, so those were the reactants. You got to figure out the reactants. Remember how burning goes. Magnesium burnt in something, and it produced something else, and it's a synthesis reaction. The afterward, the product is white and powdery and brittle. I can poke the crucible tongs in there. So before description, after description, how do you know that there was a chemical reaction? And then eventually, maybe not right this second, you're going to write the balanced synthesis equation for what just happened. The balanced synthesis equation for what just happened. Okay, part B, not nearly as exciting. Not nearly as exciting. I have copper wire. Copper wire, I can't cut this with my fingernails. I have to use wire cutters. So, oh, come on. Copper wire is still bendable, but it's harder than the magnesium. Like I had to use wire cutters. There's some corrosion on it as well as insulation, I think, unless this is uninsulated, but I don't remember. So I'm gonna clean it up. I'm gonna take the insulation off. So this is part B. It's bendable and shiny, which in science terms means it has luster That's the scientific word for it. I'm gonna do the same thing. I'm gonna hold it with the crucible tongs because, you know, heat travels in metals pretty quickly. This is not nearly as exciting. I could do this all day long. It's never gonna catch on fire like the other stuff, that it's not gonna react that great. But it's turning black. And there's some kind, it's stinky. I don't know why it's so smelly. It could just be the insulation burning off. But it's definitely turning black. So something different is happening. And I can get the little pieces of the black part to fall into the evaporator. That's getting really hot. So the afterward, it completely changed color and some of the stuff is starting to flake off. So once again, synthesis reaction, started with copper, didn't catch on fire, but it did react with the oxygen in the room, like the magnesium did. That was a hint. So that's part B. And then you will write, it's a hot evidence of a chemical reaction, and then the balanced synthesis reaction for that. We're not gonna do decomposition. Those are too big. I gotta go back in the chemical room. I'll be right back. Keys. If you wanna work on those a little bit, I'll be right back. I gotta get smaller zinc. What we're going to do for this one, it says to get a clean, dried test tube in the test tube rack. I wish this were, I can't angle this. And my little green table's gone. I put it over here. That's a little better. Okay, clean, dry test tube in the test tube rack. Add 1 pipette full of hydrochloric acid. Okey-dokey. Got my beaker, my eyedropper. Got my Florence flask. This is 6 molar hydrochloric acid. You'll understand what that means eventually. The really strong stuff, like it's in your stomach, it's digesting your breakfast right now, is 12 molar. It's about half as strong. So I'm gonna take my test tube, fill it up about halfway, it said, and then I'm going to drop a piece of zinc in. So, reactants, hydrochloric acid. Hydrochloric acid is clear. It's one of the common acids. The formula is on your sheet. Clear. Zinc is what I'm going to add to this. Add mossy zinc is what it's called because of the way it's made. It looks like little pieces of moss. I'm trying to find one small enough to go in these test tubes. It's not very caustic, which is why I can touch it. It's just a metal. But if you can see a bigger piece, this is what zinc looks like. It's called mossy. The way that they make this is they make it molten and they drop it into cold water and it solidifies into these weird shapes that look like moss on trees, and that's where the mossy word comes from. So it's zinc, and it's a silver-ish color. It's not terribly shiny. It's not very shiny. It's very solid, very hard. But that's what it looks like. And so I know I have to do this really quickly. There's actually 2 reactions going to happen here. I'm just going to preface this by saying this is what's going to happen. I'm going to take the zinc and drop it into the hydrochloric acid, and that's going to be a reaction. At the same time, I'm going to take a second test tube and invert it and capture what the reaction is making, and then I'm gonna light this on fire, what I just trapped inside of here. So it's really two reactions happening, and I can do it twice if we need to. But the first reaction, part C, the first part is a single replacement. The zinc is going into the hydrochloric acid, and there's bubbles, and it's getting hot. And I'm going to invert the test tube. Can any of you light a match? Do you know how to light a match? Anybody? Anybody? Okay, so you can see there's definitely a chemical reaction going on there. It's producing a gas. It looks like the zinc is disappearing. Okay, light the match and then don't jump. Did you hear it?
Yeah.
It wasn't very impressive blowout. I can capture more. So that's two reactions. Yeah, sorry. The chemistry space. Okay, so zinc is reacting with hydrochloric acid. That's one reaction for part C. That's one reaction. So what I'm doing is I'm trapping the product of the first reaction in the test tube, and then I'm lighting it on fire, which is a second reaction. See if you can figure out what that is. So look at what, it's all, the zinc is going away. Look, it's going away, nothing goes away. It's making something. The zinc went in the hydrochloric acid, single replacement. So the zinc is now with something, and something has been released on its own, and that's what I'm trapping. And as I'm trapping it, then we light it on fire. I don't know if I've trapped enough. Did you hear that? It usually makes a cuter popping noise, but that noise means that there's another chemical reaction. So you need to figure out what was made in the zinc being added to the hydrochloric acid, and then what am I trapping in here? It looks like nothing, it's clear. And when I'm done, there is like a liquid, like a condensation on the inside of the test tube, a clear condensation after I light whatever I put in here on fire. So see if you can figure that out. That'd be like a bonus. But it was definitely a single replacement. So that one's dirty. The other thing is, if you could touch this, this is the one that the zinc and the hydrochloric acid is in, it's hot. It's hot to the touch, not super hot. But if you feel it, let me just touch the bottom of it. It's making energy, it's changing in temperature. So that's, and look at stuff on the bottom. It's like not even zinc anymore, it's like this black, and it makes a whole bunch of heat. So that's another way you can tell that it's a chemical reaction. It was hotter, but it's not as hot right now. Cooling down, it's going back to room temperature. So that's a single replacement. Put that here. And then the next single replacement, this one's not as exciting. I need to warm it up. We'll maybe come back to this one. I'm going to warm up some copper sulfate in a beaker. It says test tube, but it doesn't work as well. So when it says aqueous, solid, liquid, gas, I trap the gas in the test tube. The liquid, I don't think I've actually used a true liquid. Oh, no, not even hydrochloric acid's aqueous. Aqueous is what most of our solutions are. So what I've done to make this means saturated copper sulfate. I took copper sulfate's a blue powder when I buy it from the chemical company, and I put it in distilled water. That's what aqueous means. I've taken a solid and I've dissolved it like Kool-Aid. So what I'm gonna do for this next part, it doesn't say to do this, but I know from experience, it tends to work better. I'm gonna heat up the copper sulfate. Reactions usually work better when they're a little bit warmer, just because the particles bump into each other more. And so if they can bump into each other more frequently, then the reaction happens faster. So I'm gonna let this one go for a little bit. This is supposed to be part D. We're gonna come back to this. Plus, copper sulfate, I didn't put the suffix on the sulfate. That's what that should be for number 1. And I'm gonna throw zinc in there in a minute and you'll see what happens. So we're going to jump on over to E while we're waiting for that to warm up a little bit. I have silver nitrate and a salt water mixture. Once again, okay. And some other things living in the salt water. We'll worry about that later. Salt water, silver nitrate has to be kept in a brown bottle because sunlight will decompose it. It'll decompose back into silver. So I have to keep it in a brown bottle. I'm gonna go get some more pipettes and I'm worried about I might go get cleaner salt water. That's Beckley water. That's what I didn't use distilled water on that. Pre-made salt water. So this is hydrochloric acid. Not really want the copper sulfate to boil. This is salt. This is silver nitrate. That go a little bit longer. So the silver nitrate is a clear liquid. Salt water, clear liquid, unless it's Beckley water, in which case brown stuff comes out of it, but that's okay. So those are the reactants. It says to add 1 pipette full of silver nitrate to a clean dry test tube. Okay, silver nitrate, 1 pipette full, give or take. So it's a clear liquid. That's getting too hot. Move it over here. Okay, to the silver nitrate, salt water, I've already made the mixture, and it's a clear liquid as well. This happens really quickly. When I put it in, it makes a white powder. And that's kind of how you know that it's a reaction. 2 clear liquids just made a precipitate. That's what we called it. I'm gonna let this sit, and by the time you're out of here, all the white powder will go to the bottom because of gravity, and you'll see a clear liquid at the top. So this is a double replacement or double displacement. You had 2 clear liquids, they made a white powder. I'm gonna put that here. That was part E. I'm gonna jump back to part D. That's my fairly warm copper sulfate. I wanna make sure that we have that. So the copper sulfate is a blue liquid. That's copper sulfate. And I'm adding to it zinc. And the zinc is still silver, not very shiny. This is a single replacement. Trying to get smaller pieces so it'll happen faster. This one takes a while. So it's going, there's little tiny bubbles. You can see that a gas is given off. It's nothing, it'll sit here for a while and it'll get more fascinating as time goes on. But that's a single replacement. Okay, and the last one, copper sulfate. And hydroxide, and that's why. Yeah, this is sodium hydroxide. That looks gross. Well, it'll be what it'll be. I'll make that. Need another beaker. It says sodium chloride. I'm getting rid of this. I need sodium hydroxide, which I didn't bring out here. So I've got more copper sulfate, which is that blue liquid. This one just isn't as concentrated. So for the last one, copper sulfate solution, just like that one, is not quite as concentrated. Blue, kind of transparent, definitely a liquid. Sodium hydroxide is what I'm going to add to this as soon as I find it. Sodium hydroxide is also a clear liquid. This is going to be a double replacement. So you've got sodium hydroxide, clear liquid, copper sulfate, a blue liquid, get a clean, dry. Which one does it say to put in first? It says add 1 pipetful of copper sulfate to a clean, dry. Okay, so it's going to go in first. Copper sulfate. Clear, bluish color. We're going to add to that the sodium hydroxide, if I can find a pipette that works. Okay. It makes a gel. I'll pass this around. You really can't hurt yourself with this. But it makes a, it's really hard. I'll probably throw the test tube away. It makes this gelatinous pale blue stuff. I guess it's a solid. But I'll pass it around. You can kind of tip it a little bit and see it's not moving very much. I'll send this with it. You can kind of poke at it. It's thicker. I'm not going to do that. That makes a mess. It's there's particles in it. If the copper sulfate were more concentrated, like that stuff there that I'm using, it would be really thick. But you can see there's like little particles in it. And there's like bubbles. It almost looks like a blue jello. But that's what it's doing. It's a gelatinous solid, like a different color. So that's how you can tell that there's definitely a chemical reaction that's happened. Because you had 2 liquids that became a solid. So that's all of them. The copper, sulfate, and the zinc. Back to this one. This was letter D. I don't know what's happened. There's bubbles all over the place. But little pieces of copper will start to float on the top. So maybe I should put a smaller piece of copper, but that's what's happening. As you leave, one at a time when that happens, there are little pieces of copper that are forming out of the copper sulfate. So the zinc is replacing the copper, and there's pure copper being formed as this is happening, and that's what's coming on. And you can tell the copper in color and everything, but little tiny flakes are starting to form because it's warmer, and over time, more of it will form. You'll get pure copper out of the copper sulfate. So now, do we understand the observations before, the observations after, how you knew that a chemical reaction occurred? Some of them were not that dramatic. And then the balanced chemical equation for each one. So let's do one together. Let's do the zinc and the hydrochloric acid. So the zinc, I took a piece of zinc and I stuck it in hydrochloric acid. So if this were a homework problem, you would look at your activity series and see if it's going to happen, but you know it happened. But you could check the activity series anyway if you wanted to. Zinc was a solid, so if you wanted to get real technical about this and put the actual phases, you could, you don't have to. Hydrochloric acid is actually aqueous. To make hydrochloric acid, they actually take hydrochloric gas and bubble it into water. So this is a single replacement. And there was a reaction, the bubbles, the heat, you could definitely tell there was a chemical reaction. So the zinc came in and bumped out the hydrogen. Zinc is a +2 charge. Chlorine, -1. This is the black stuff that was forming in the water. And then the hydrogen is a gas. That's what's by itself now, and it's diatomic. So I was trapping hydrogen in the test tube, and then we lit it on fire. See if you can come up with the second reaction that happened during that part. I trapped hydrogen gas in the test tube and then lit it on fire. So see if you can figure out what the second reaction was that happened during that part, and include that as well. And if you get it right, I'll give you some bonus points. So by Friday, your observations, how you know it was a reaction, and a balanced chemical equation for each part. That's all I want. You can turn it in by Friday night at midnight. That'll count as an experiment grade. Do you have any questions, or you want to see anything over again? Okay, I think I'm going to make a better video third period because this one was me running around a lot. So.